or the subject the same degree of difficulty. Our first one here is a simple mass conversion. We have a sample that's 5.5 grams, and we simply want to express that in milligrams. Now, you know, you can do this in your head. If we've done this enough, you can. You know that every gram has 1,000 milligrams. You know that. But what we're going to do is do it using the given ratio method. So our given here is going to clearly be our 5.5 grams. So using this method, we would just write that. Secondly, we say to ourselves, we want to go from grams to milligrams. Well, there are 1,000 milligrams in every gram. So our ratio has to be 1,000 to 1. So we write a ratio. We know that we've set it up right because we have grams here and here, and they're going to cancel. Now all you have to do is multiply the 5.5 times 10 to the third, and that's the answer. 1,000 milligrams in every gram. So if you have 5 grams, you have 5,000 milligrams.
How did you come up with the 10 to the third?
10 to the third is 1,000. 1 times 10 to the third is 1,000. Any questions? All right, 2 and 3. On the actual exam, I will simply choose different elements, but the table will kind of look like this. What you have to do is identify the element on the periodic table. Every exam will have a periodic table, so I'll give you one. And then simply identify the missing parts of our table. So here's our table. First of all, we're looking for magnesium. Magnesium is Mg. It's right here. So we look and we see its atomic number is 12. We say to ourselves, if the atomic number is 12, that means there are 12 protons in the nucleus, right? Therefore, number of protons, 12. Now, every proton has a positive charge. So we have 12 positives in this atom. We look over here and we see we have 10 electrons. Every electron has 1 negative charge. So we have 2 extra positive charges going. Therefore, the charge on this thing, plus 2. Finally, mass number. Our mass number is 24. Remember, mass number is protons plus neutrons. If 12 of those are protons, the other 12 must be neutrons. Lead. Lead is down at the bottom here. Its atomic number is 82. So how many protons does it have? 82. It has 82. Now, we're given in our table that we have 125 neutrons. Remember, mass number is neutrons plus protons. So pull out your calculator. 82 plus 125 is 207. Finally, our charge is plus 3. That means we must have 3 extra protons. 3 more protons than we do electrons. Therefore, 82 minus 3 gives us 79 electrons. Any questions on this type? The one on the exam is going to be just slightly different. For at least one of these, I've written it with the actual element missing. So you have to look at whatever's given, figure it out, and write the symbol.
What if it was a negative charge?
No.
Would that number
Then you
increase,
add
the other one would increase?
We have 3 more protons than we do electrons. Protons are positive. We have 3 more. Therefore, it's got to be 82 minus 3 to get the electrons.
I know, what if your charge is a negative and you
That
have
means
more
you have more
electrons?
electrons. So you look at the number of protons and add. If this had been a minus 2, you would add 2 electrons.
To,
Like if that was a minus 3, you
Mhm.
would instead have 85.
81.
You put 85, yeah.
On the protons?
Yeah.
Okay, so it's negative, it goes to the protons, if it's positive, it goes to the electrons.
That's right. All right, let's do ammonium hydrogen carbonate. Now we'll talk a little bit about nomenclature 2 or 3 times as we work these problems. This is clearly an ionic compound. Remember, ammonium was our polyatomic cation, the only one we have to know. Carbonate, the parent of the carbon family, is CO3 minus 2. And hydrogen simply means we have a hydrogen with this plus charge on the carbonate. So we approach it this way. Ammonium, we remember, ammonium is simply NH4 plus, our polyatomic cation. Carbonate, again, this is something you have to remember. The carbonate is simply CO3 with a 2 minus charge. Now we're going to put ammonium and carbonate together, but remember there's a hydrogen. Hydrogen brings in 1 positive charge. So we have a positive charge here, 1 here. So we'll do this. There's the ammonia, there's the carbonate. All we have to do to write the formula is to stick in the hydrogen. The hydrogen, remember, is actually attached to one of these oxygens. So this changes carbonate from minus 2 to minus 1. Hydrogen is a plus 1. So this goes from minus 2 to minus 1. This is plus 1, and that's our formula. This is also called bicarbonate. Sodium bicarbonate, baking soda, same sort of thing, except we have a sodium in front, and again the HCO3. All right, we're looking for an element on our periodic table. We are given that it has a charge of minus 2, that it has 18 electrons, 16 neutrons. All right, here's our periodic table. If this thing has a charge of minus 2, and it has 18 electrons,
It's going to have 16 protons.
that's right. It must only have 16 electrons because it has 2 extra electrons. So that's the real whole point of this question. Make sure you can figure that out.
You said it again, I'm sorry. Can you repeat that for me?
Okay, I will. This element has 18 electrons. Has 18 negatives, right? and the net charge is -2. That means there are 2 more electrons than there are protons. The protons are positive. So it must be 16 protons and 18 electrons, 2 extra electrons. That gives it the charge of -2. So what you do is look at your periodic table, and you're looking for something with 16 protons. And oh my goodness, it's sulfur. Atomic number of 16, but it has 18 electrons. So 16 protons, 18 electrons, -2. All right, so to write the atomic symbol, we start off just with the S. Remember, in an atomic symbol, the atomic number, that's the number of protons, goes down here. The mass number goes up here. Now, mass number is protons plus neutrons, right? So we have 16 protons, 16 neutrons. We're looking at 32. And finally, to make the symbol complete, you have to put the charge. If there's no charge, you just leave it blank. If there's a charge, you put it on afterwards as a superscript, and that's -2. Any questions? Again, the key thing to solving this problem, the key thing, 18 electrons, but 2 of them are excess. Yeah.
You got 32, right? So you added 18 and 16, and you subtracted that 2.
No, 18, not 18. It's protons plus neutrons. The protons have the atomic number.
Which is 16.
16
Plus
plus
16.
16, 32. All right, the next guy here was a simple density table. Most of you have done density 1, which basically is just this table. We are given a volume and a density, and we simply have to calculate the mass. Right? All right, remember, density is mass divided by volume. You get to bring a 3x5 card. You can write that on there if you want. Mass divided by volume. I'm sorry, what? Yeah. Oh, I told you that lots of times. Now, everyone gets to bring a 1 3x5 card.
Maybe the
3 inches by 5. No. 3 inches by 5. You can do both sides. You can put anything in the world you want on there. It really teaches you to write small. Okay, so anything that you have trouble remembering, put on your card. And everybody will get a periodic table with their exam.
Does it have a name like mine on the bottom?
All right, so density is mass divided by volume. Here we have to simply solve for mass. Do this algebraically. Volume times density is mass. So we just plug in our numbers here. Our volume is 6.9, our density is 1.4. We just multiply these together. Remember, we're dealing with 3 digits here, 3 significant figures. So we write it as 9.84. Just remember, density is mass divided by All right, our favorite, polyatomic ions. Remember, for polyatomics, you simply want to focus on the parents. All right, so the eights. Make sure that you kind of know the eights or the groups. Which of the following names and formula is incorrect? Phosphate, PO4, -3. That's true. Let's skip B. Aluminum. Aluminum is a group 3 metal. Therefore, it's a +3, isn't it? Oxide. Oxygen is a group 6 nonmetal. It has to gain 1, 2 electrons to get over to the noble gases. Therefore, it's a -2. Nitrate. This is the parent for the nitrogen family. NO3, 1 negative charge. The one that is wrong is sulfate. First of all, sulfate is SO4 -2. Persulfate would have 1 extra oxygen, remember? Per is 1 more.
So would be 3. Sulfate?
Persulfate doesn't exist,
Oh.
but sulfate is SO4 with 2 negative charges. Sig figs. There will be significant figure questions. First of all, we look at this number and we say to ourselves, does it have a decimal point? Well, yes, it does. That means that if it has a decimal point, that all of the trailing digits are real. That was in our measurement. But none of the leading digits are real. So, we simply look at this, we say all of the leading digits have to go, but everything back here, after we get to real numbers, they stay. So it looks to me like there's 1, 2, 3, 4, only trailing zeros count. Scientific notation. What's the one thing, well, one of the things that we remember about scientific notation? That the coefficient here, these guys out here, this is the actual measurement. So all of the digits in the coefficient are real. Then we put the exponent, they're not real. But all the digits in the coefficient are real. So all you have to do is count the number of digits. 1, 2, 3, 4, 5. 5 significant figures.
So the -8 doesn't count?
Nope, doesn't enter at all. Those are leading zeros, actually. Or trailing zeros, but they don't count. All of the significant figures must be in the coefficient. Yeah.
So if it was 84,000, would the significant figure still be 5?
Yeah.
Since it doesn't have any decimal.
Right. No. If you just had the number 84,000 with no decimal, no, there'll be only 2. There's no decimal. Trailing zeros go. There's only 2. All right, here we have a number, and we want to put this into scientific notation. Remember when we put the number into scientific notation, want to move our decimal from where it is to in between our first two real digits. So what we're doing here, here's our number. We're going to have to move it from here to between the 1 and the 3. That's 7 places, and we're going to the right. That means this is a negative exponent. And the exponent is -7. We will wind up with 1.3 as our number, as our coefficient, and 10 to the -7 as our exponent. We move it over 7 places to get 1.3. The one that works here is simply that. Any questions? All right, let's talk about electrons. Silicon. Up, down arrows to complete the table for the electron configuration. All right, step 1. First conceptual step, I suppose, is to remember that, well, first of all, here's silicon right here. It's in the 3rd period. That means that everything above it is full. Everything above it is full. Every orbital, every blank on this table can only hold 2 electrons. So, we're here. So our first period, we can hold 2 electrons. This is going to be 1 up, 1 down, and it will look like that. The first period is full. Second period, we're going to put 2 electrons here in the S block. Again, it's full with 1 up, 1 down. Now the P block here is also full. And we have 1, 2, 3, 4, 5, 6 electrons in there. They're going to be paired as up-downs, and they'll look like this. All right, on to our 3rd period. The first 2 are going to go into the 3s. There are 2 of them, so they fill it up. And that gives us 1, 2, 1 up, 1 down. Now we have our P block left here. In our P's, we have 1, 2 electrons, right? Only 2. The rule is electrons all go in with the same spin, 1 at a time. Once you get filled up, then they start to pair. So, our P block is simply 2 electrons, both with the same spin. It could be up or down, but with the same spin. And if we had more than 3, we would start to pair. Now the key things to remember here, because we're in our 3rd period, that means that 1 and 2 must be totally full. Remember that, that's simple. We're in our 3rd period, so we're over here in the P's, so the S's have to be full. That's 2 more. And as we put these in, remember they go in 1 at a time, same spin. Once you get 3 in, then they start to pair up with opposite spins. Any questions? All right, the next question is, do I know how to use my calculator? A simple multiplication involving exponentials. Virtually every scientific calculator will have a function that lets you enter exponents. Multiply them together, you get an answer in scientific notation. Now, if you don't want to do it that way, you don't have to. You can use a four-banger. The way you do it is what we're going to talk about here. Step one, you're going to look at your two coefficients, this guy and this guy, and simply multiply them together. So 2.31 times 4.38, 10.1. Now I've rounded this to 3 digits because we have 3 digits that we're working with. Secondly, we remember the rule. If it's multiplication, the exponents add. If it's division, the exponents subtract.
Say that
Well,
one more time, please.
This is multiplication. So
Okay.
the exponents add. Division, they subtract. So here we have 10 to the 2, 10 to the minus 12. Add them together, we get 10 to the minus 10. So at this point, we can write our answer. We simply take our coefficients, 10.1, and our exponent minus 10, and we can write that. But we look at that and say, wait a minute. We want our decimal point to be here, in between the first 1 and 0, between the first 2 digits. So that means we're moving to the left here, 1. When we move to the left, that's a positive, isn't it? So instead of 10 to the minus 10, we move it 1 to the left, it's a 10 to the minus 9. Now, I will say this over and over and over again. The point of this exercise is to teach you to use your calculator. Because we'll do this a lot later. You know, this is a skill that you're going to need in the next chapter or 2. So make sure you know how to do it. Punch this in your calculator. This is the answer you'll get. But if you don't want to do that, you can do it the long way. Get the same answer. All right, remember physical and chemical changes. Physical changes, you're just changing, the appearance of a substance. Changing its state. Chemical change, you're making a new substance. That's the thing to remember. With a chemical change, you make a new substance. Physical change, you don't. So let's look at this. Physical changes are always accompanied by a change in state. Whenever you see the word always in a question, it's always wrong. Okay? So that's right. Physical changes result in the formation of homogeneous mixtures, not new compounds. Well, they don't make new compounds, but homogeneous mixtures, remember, are solutions. And you can do physical changes that don't wind up being a solution. You can melt something, boil something. It's not a solution. So that's wrong. They always produce new elements. Well, boy, that would be nice. Turn lead to gold, that doesn't work. A and C, forget those. None of these are correct responses. With physical change, you always wind up with the same substance. With chemical change, you always wind up with one or more new substances. Any questions?
So what's an example of a physical change?
Melting ice is still water. Nomenclature, there are 2 or 3 nomenclature questions on the exam. When you see a question and you say to yourself, oh my gosh, it's a nomenclature question, what's the first thing you have to say? First thing you have to say, is this a molecular compound or is it ionic? The way to answer that is to say, does this have a metal in it? Does it have a metal? If it has a metal, it's ionic. Why is that important? Because if it's an ionic compound, you don't use multipliers. If it's a molecular compound, you do. So we look at here, we have phosphorus and oxygen. Phosphorus is here. It's in group 5 under nitrogen. Oxygen is group 6. Both of those are non-metals. Yeah.
Moleculars are non-metals,
Right. Moleculars are non-metals. Anything with a metal is ionic. So we are going to use multipliers. So we look at these. We have 2 phosphorus and 5 oxygens. We cannot use phosphorus oxide because there are no multipliers. We only use the Roman numeral with ionic compounds that are transition metals. So that's wrong. The prefix for 2 is di. Prefix for 5 is pent. Diphosphorus pentoxide. If we leave the di off, that's wrong. If we leave the pent off, that's wrong. Diphosphorus pentoxide. Step 1, it's molecular. We need multipliers. Only time the multiplier doesn't appear is if there's only one of the first element.
So if it's here, it's metal, it's a metal.
Those are transition metals, right?
Those are ionic of these.
It's this little group right here.
Uh-huh.
Those are your nonmetals and semimetals.
Here.
Right. Here we have copper 2 sulfate. How many oxygens do we have? Well, we all remember that sulfate is a -2 anion, right? SO4 -2. Copper 2, by its name, has a +2 charge. So we have 1 sulfate for every copper 2. The compound simply looks like this. How many oxygens? Well, by gosh, we can all count 4. Any questions? Copper 2 is a +2, sulfate's a -2. They pair up 1 and 1, 4 oxygens.
So they delete each other.
Hmm?
The twos.
That's +2, -2.
So they,
one copper, one sulfate.
so is that why they don't show there as a 1 and a?
Right, well, you could do the 2 and 2, cross it over, but you'd realize you would have to reduce it to the lowest whole number ratio. Another density problem. Here we're looking for volume. Exactly the same problem we had before, except it's not a table. So what you do is you sit back and say, density is mass divided by volume. Here we have to solve for our volume. If we bring volume up and density down, that's going to be mass divided by density. Simple algebra. So, to solve this, what do? We take our mass, which is 58.3, our density, which is 0.841, divide them, and we get 69.3. Simply mass divided by density.
The mass divided by the density? Just
Mass
the
di-
volume, no?
Volume is mass divided by density. You're going to bring volume up, you're going to bring density down.
But where do you have
We're
Mass
given,
up there.
we're given mass,
that's the mass?
that's the mass, 58 grams, and that's our density. You will have the opportunity to draw a Lewis structure on your exam. Here we're going to practice by drawing the molecular compound BH3. So you start off by looking at your periodic table. You need to find boron and hydrogen. Boron is here in the third group. That means it has 3 valence electrons. Hydrogen is here in the first group. That means it has 1 valence electron. So you start off by drawing your boron. 3 little dots around it. We have 3 hydrogens. They each have 1 electron. So they all go around our boron. Now, in order to form a bond, we use 2 electrons, 1 from each. So we can form 3 bonds here, scooching them together like that. Now, if you left it like that on the exam, that would be perfectly fine. Or you could use the dash shortcut and simply put in line bonds like that. Now remember, boron is an exception to the octet rule. The octet rule says that every element in a compound wants to have 8 electrons around it. So it's just like the inert gases. For boron here only has 6. So it's an exception. But this is still a totally valid structure. Any question? All right, another Lewis question. We're dealing with ammonia. how many valence electrons will there be around the nitrogen? We just saw an exception to the octet. Okay, so let's look at ammonia. Nitrogen is here in group 5. Hydrogen, again, is group 1. So we have 5 valence electrons, and we have 1. We'll put our nitrogen in the middle, and put 3 hydrogens around it. Now to make our bonds, we're simply going to pair up these guys, and these guys. So we're sharing these electrons, these and these. How many are around the nitrogen? This is the true octet rule. There are 2, 4, 6, 8 electrons around our nitrogen. Now I asked this question once on an exam, and I said, how many electrons are around the hydrogen? And you'd be amazed that 60% of the people said 8. No. Remember, hydrogen is in our first period, so it can only hold 2. And it's got the 2 that it needs right here.
So each one has 2.
Each one has 2, and the nitrogen has 8. Another nomenclature. What element is K? Potassium, right? Phosphorus is P, potassium is K. All right, so we look at this and we say, what's the first thing we say to ourselves? This is ionic or molecular? Is potassium a metal?
No.
Hello,
So it's
right there.
C.
Group 1, it's a metal. Phosphorus isn't. Potassium is a metal. Everything here up to our magic line is metal, except hydrogen. Our magic line goes through here. All of these guys are metals. Okay, so if it's a metal, we don't use multipliers.
Which is the di and the mono and all that.
You don't use those, right? You don't.
That's what was confusing me in
Yeah,
the
so
tutorial.
that's it. You don't use it. So we look at this and say, we have potassium and we have oxygen. What is this? Potassium oxide. The only time you want to use a Roman numeral is if you're in the transition metals. So 1 and 2, 3, forget.
So wait, you don't use the multipliers in this one?
No, because it's ionic.
Oh,
The rule is molecular gets multipliers, ionic does not. This is multipliers, multipliers, multipliers. Forget those. It's not a transition metal, so forget the Roman numeral. It's simply potassium oxide. And our last guy here, we're looking for a compound where the cation has a positive charge. So what, in your mind, what do you think to yourself? If it's going to be a +3, what group in the periodic table is it in?
3.
3. How simple can that be? If it's a +3, it must be in group 3. So, look at this. Calcium, magnesium, they're both in group 2. They're plus 2. Ammonium, we saw that earlier, that's a plus 1. Phosphorus trichloride, phosphorus and chlorine, they're both nonmetals. They don't even belong in this question. Only one that works is aluminum.